Okay, section 3.3, it's on page 221, talks about how a derivative affects the shape of a graph. So we want to get this first diagram out of the way, and then we're going to elaborate on that and repeat it for the second derivative. So suppose I have a function, something that looks like this. If I look at where the slope of the tangent equals 0, I'll say the derivative is 0 right there, whatever that point is, about right there, and about right there. So at these three values, let's call this A, let's call this B, and let's call this C. A, B, and C. Something that we're going to use all throughout. If I look at the function to the left of this 0, it's increasing. So I was going up. And then to the right of that, I was coming down. That's the definition of a maximum. So F was going up to the left of that, and F was coming down after that. If that's the case, well, there it is. That looks like a maximum, right? That's a peak. And it continues on. When I get to this point, I am standing still, but then after that, I'm going up. So if I glance at this left side of this, well, hey, that looks like a minimum. And to the right of that, we're coming down. And if F is decreasing, then that would be a maximum as well. Now, one exception. Suppose the graph terminates like this. Now, at this point, this new point, D, I could say the slope equals 0 right there, so that counts. However, to the right of that, I notice the function keeps on decreasing. So, I could say that's a minimum easily. I could say that's a maximum easily. But this is not a maximum nor a minimum, and this is not a maximum nor a minimum. Another thing I didn't talk about yet, let's get that out of the way. If I look at the left of this 0, so we said the slope of the tangent equals 0 at this point. If I look at to the left, as the function is increasing, I notice the slope of the tangent is positive. To the right of that, I notice as the function is decreasing, the slope is actually negative. Right? And when it increases after that, I notice if I put a line, the slope of these tangent lines are all positive. And then the slope of these tangent lines are all negative. And then it's negative again. So I can conclude, and this is true, whenever this derivative is positive, the function is increasing. Wherever the derivative is negative, the function is decreasing. So derivative is positive, function is increasing. Derivative is negative, function is decreasing. And that's really what I'm going to be doing. I'm going to be playing with this more than anything. And to demonstrate that, I want to look at the first problem. Problem number 6 on page 228. It says, the graph, this is not F, oops, this is the graph of the derivative, is shown. On what interval is the function increasing, and at what values of x f has a local maximum or local minimum? Well, let's see. The best way to do this is really, this line will do it for first and second derivative test. So if we go ahead and look at, since this is the derivative, I need to know where does the derivative equal 0, right there. So again, this is not f, this is f prime. At 3, I'm sorry, that's not 3, that's 5. And at 7. At those points. And I notice to the left of this, so between 0 and 1, this derivative is positive. Between 1 and 5, the derivative is negative. Between 5 and 7, the derivative is positive, and then after that is negative. And I already established if the derivative is positive, the function is increasing, the derivative is negative, the function is decreasing, and it turns out that's how this looks. So to answer part A, I would say f, and this is how we note increasing, from 0 to 1, union with 5 to 7. F is decreasing from 1 to 5, union with 7 to 8, it seems, because that's what this graph terminates. B, well, I have a maximum if it's a peak right there, it seems. F yeah, okay. So at x equal maximum of f at x equal 1 and 7. Do we see that? And minimum of f at x equal, it seems, only 5. And those are local maximum of the numbers. And that's pretty much how it works for the first derivative test. And the following two theorems are pretty much reinforcing what we just learned. It says if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. We got that. We know what the critical numbers are. In this case, 1, 5, and 7 are critical numbers. It says if the derivative changes from positive to negative, you have a maximum, negative to positive. If it's minimum, well, this is much easier to use than to try to memorize that. Now, something I want to point out, I want to go back to this graph and elaborate on the second derivative. Second derivative is a bit trickier, and this is really what the second derivative measures. Something we didn't pay attention to, let's pay attention to it. Actually, let's leave that one alone. Let me go for... okay. Not that one either. Let's talk about this one. This should do it. Okay, look at this function. If I'm glancing at this graph, come on. Got it. If I'm looking at this graph, now I notice slope is 0, increasing, 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 no longer increasing. Do you see that? When I started looking at this, that was the slope of the tangent. Increase, that's bigger, that's bigger. But this is not bigger, and this is definitely not bigger. When I was coming down on the right hand side, if I looked closely at those, I'll notice that, well, look, the slope is 0. This is like the tip of my car, and I start going downhill. I'll notice that, well, it's getting faster and faster. But do we agree that at a given point, the tip is going to start? Do we see that at a given point, the tip of the car, the point of it, will no longer be pointing downward? It'll start leveling off. You're moving forward, but you're no longer accelerating. The point where that happened, the point where the tip of this arrow, instead of going down, it starts leveling off, that right there is called an inflection point. I'll give you that in the definition. The easiest way to see those is for you to think of the graph as a parabola. If this was a parabola, shouldn't that look like this? And if this was a parabola, shouldn't that look like this? And if this was another parabola, and if this was a parabola, and of course if this was a parabola. So the point is, when you want to figure out the second derivative, it's a bit trickier. You want to figure out, if I was on this yellow shaded part, I broke off from the yellow and picked up on the blue. That right there is an inflection point. And if I was on the blue curve, if I was running as a parabola, the point where you think you broke off and you went to the pink, that's an inflection point. And if you are on the pink, this parabola should continue down, but at a given point, you switched on, and so on and so forth. Right? So I'll show that as well on a couple of examples. I'll show you graphically, and of course algebraically is where the busy work is. And here's another definition that says, well, pretty much what we covered. It says, concavity test, if the derivative is positive, the graph is concaving upwards. This is what they mean by that. We call this concaving up because it looks like this. And for that, the second derivative is positive. So we're going to do pretty much the same test as we did right there. And that's going to determine for us the same idea as first derivative test. And if I look at this right here, this looks like it's concaving down. So concaving up is like a smiley face. Concaving down is like a upset face or sad face. And it turns out, wherever the graph is concaving up, the second derivative is positive. Wherever the graph is concaving down, the second derivative is negative. If you switch from concaving down to concaving up, that's an inflection point. If you switch from concaving up to concaving down, that's an inflection point. But if you concave up and then concave up, it's useless, kind of like what we did here. And that's pretty much how we're going to play this game. The goal is for you to be able to sketch the graph of any of those. And we want to start with an example. Looking at problem number 10, it says, find the intervals of which f is increasing and decreasing. Well, A, I need to take a derivative. The derivative is, and this will be 8x 6 x squared minus 18x plus 12. Where does that equal 0? So we have x equal 2 and 1 as critical numbers. I could do my test right there and figure out everything that's needed for that problem right there and decide where f is increasing and where f is decreasing. Well, let's see. If I take 1 and I take 2, remember, this is the derivative and this is f. I just want to know the plus or minus. If I pick 0 and I put it in either of those, if I put 0 right there, that's positive, 12. If I put 1.5 as a test point, 1.5 minus 2 is negative. 1.5 minus 1 is positive. That makes it a negative. And if I put 3, that's positive times a positive. So f is increasing, decreasing, increasing. I would say that. I would say f is increasing from negative infinity to 1, union with 2 to infinity. And f is decreasing from 1 to 2. Not only that, it seems I have a maximum, local maximum, at 1. And if I plug 1 in the original for f, f has a maximum. I have a maximum at 1, and what is that? 12, 14 minus 12 is 2. And it seems I have a minimum, local minimum, at 2, and if I plug 2 in, I will get a 1. So I already know what I have. Actually, I'm going to finish this in the next video.